effect size when doing meta-analysis. So what is the effect size? We hear about this term repeatedly in the literature and in research studies. Effect size is a statistical measure that quantifies the magnitude or the strength of a relationship between two variables. One of these variable is experimental variable, and the other variable is the group variable, or two variables, one of them is exposure, the other one is the outcome. The effect size also quantify the difference between two groups. That is used when the two groups are normally distributed and they have a continuous data in it, and the mean is determined for both groups. Then the difference between the means for these two groups can reflect or represent the effect size. So the difference between the two groups measures how large or how small is the difference between the two groups. Whether one group have a higher mean and a second group has a lower mean, then the difference will be large. If the means for the two groups are close to each other in a value, then there is a small mean difference, and that mean difference is valued when performing meta-analysis, and it will reflect the effect size, as sometimes it is called as standardized different differences between means. And also the effect size can estimate the likelihood of an event occurring in one group relative to another. So for the likelihood, that can be used and estimated when the variable or the outcome is binary or dichotomous, categorical, have two categories in it. Then the likelihood of event occurring in one group relative to another one is estimated, and that can be measured to give an effect size value. So for effect size estimate, for the first option is that when the data are continuous and then a correlation is established between the two variables, then the value of that correlation represent the effect size. When the mean is determined for the two groups and a difference is calculated, then that can represent the effect size. And when the data are or the outcome is categorical or dichotomous, then the likelihood of an event is estimated, which is the odd ratio, and that can represent the effect size. So the effect size will provide standardized way to evaluate significant observed effect in a study or experiment. So in a study that have two groups, one is control and the other is a treatment or experimental, and then a p-value is generated and found to be significant, that is not enough, but the effect size will provide a standardized way to evaluate that significant by giving a value which is for the effect size. So the effect size will determine the extent to which the independent variable, which is in some cases can be a treatment or intervention or experimental, that can influence dependent variable, which is an outcome. So to which extent these treatment conditions affect the outcome, and that can be represented by an effect size. So a larger effect size suggests a stronger relationship or a larger differences between variables based on which measurement has been used, whether correlation or differences between the means. However, for a smaller effect size indicates weaker relationship or smaller differences between control and treatment. So the effect sizes of several studies are combined from multiple studies to produce an overall estimate of the effect size in meta-analysis. So when performing meta-analysis, most likely the effect size is estimated, and it is combined all together from several studies to eventually calculate the overall or the pooled estimate of the effect size. So the common effect sizes that are in practice, the first one is the standardized mean difference, which is abbreviated as SMD. The second one is the odd ratio. So the first one is used when the variables or the data are continuous and the mean is determined for two groups. Then the means for both are standardized. The second one, which is the odd ratio, is used when the outcome is binary or categorical. So odd ratio OR will be used, or a risk ratio can be used, or a hazard ratio, which can be used when there are two variables. One of them is a time variable, the other one is an event, such as death or living. So it is mainly used for survival analysis. And finally, the other effect size is the correlation coefficient based on the Pearson correlation coefficient. These are the 5 major common effect size that can be used in a meta-analysis. So the first type, which is a standardized mean difference, used this one of effect size is used when the combined study measures or measure the same variable but uses different unit of measurements. So 2 different studies or 3 different studies, each one of them used different unit of measurement but the same variable or the same outcome, then the standardized mean difference will be used to determine the effect size. So the standardized mean difference is the effect size, and this can be calculated by dividing the difference between the means for the 2 groups by the pooled standard deviation of the both groups. So you take the standard deviation for both group and then the mean differences between the 2 group, and then you divided the mean difference to the pooled standard deviation. So this is one of the effect size. Another one, which is the odd ratio. What is an odd ratio? It is used when the outcome variable is binary, so it is categorical, it has 2 levels in it. So the odd or the odds ratio represents odds of one event happening, or the likelihood of one event happening in one group relative to the likelihood or the odds of the event occurring in another group. A third effect size is the risk ratio. This is used when the outcome variable is dichotomous, which has only 2 levels in it, such as life, dead, yes, no. So the study design include, or designs include in it a control group, then the risk ratio can be used. So the RR represent the risk of an event occurring in a treatment or experimental relative to the risk of an event occurring in the control group. And for a fourth type of effect size, which is the correlation coefficient based on Pearson correlation, it is used when the combined or multiple studies measure the relationship and the strength of the relationship and the direction of the relationship, whether it's positive or negative, between two continuous variables. So it's represent the strength and the direction of this relationship between the two variables, whether it's positive, both variables increased when one increased, the other increased, or it is minus relationship, inverse relationship, in which one variable increases, the other one decreases. So the effect size can be continuous, can be calculated when the outcome is continuous. Then the mean difference can be calculated, and that will represent the effect size, or a standardized mean difference can be calculated. There are several subtypes for the standardized mean difference. The first one is the Hedges G, the second one is the Cohens D, and the third one is the glasses delta. So those are the most common SMD used or in practice when performing meta-analysis. However, when the outcome is binary, which is not continuous, then the research study will use an estimate effect size, which is the odd ratio or the hazard ratio or the risk ratio. So let's start with the first SMD, which is the Hedges G. What is a Hedges G? It is a statistical method that determines the standardized differences between two means. So it is an SMD, and it is used when the data are continuous. So the variables are both continuous, and then a mean is measured or calculated for each variable. Then the difference between these means is calculated. It is similar to Cohens D and glasses delta effect size, but Hedges G is preferred when the sample size is small. So when you have a small sample size, it's preferred to use Hedges G than Cohens or glasses delta. It provides this Hedges G, which is an effect size estimate, provides more accurate estimate of the population effect size. It is calculated. How do we calculate the Hedges G? By taking, first of all, the difference between the means of the experimental and the control groups and dividing it by corrected standard deviation, which takes into account the sample size and the number of degrees of freedom. What does that mean? It means that the main differences between the Hedges and Cohen D is that Hedges uses pooled weighted standard deviation instead of pooled standard deviation when performing meta-analysis. So the equation for Hedges G is equal to the mean for the first group minus the mean for the second group divided by the standard deviation, which is in this case the pooled and weighted standard deviation. So this is the formula or the equation for how to calculate Hedges G, which is an estimate of the effect size. So larger value for Hedges G means that the two variables, the difference is large. Smaller one, the difference is small, but This Hedges is standardized. So Hedges G values ranges from negative to positive. So it can be positive, it can be negative, since we are subtracting means of groups. So if the value is equal to 0, then that indicates no differences between the two groups being compared. If the value is positive, then that indicates that the first group have or has a higher mean than the second group. And if the first group have a mean lower than the second group, then the Hedges G value will be minus. Now, this is for Hedges G. Moving to the Cohen D, which is similar to the Hedges G, but with certain variation. It is again an effect size estimate. It is a statistical method that compare the mean of or the means of two groups. It is calculated by finding the differences between two means or means of two groups, and dividing that by the pooled standard deviation of two groups. So the Hedges G is similar to this, but that's Hedges G is divided by the pool weighted standard deviation. The Cohens is just by the pooled standard deviation. The Cohens D is used to determine the effect size of a particular intervention or treatment compared to control. It is often used in meta-analysis for comparison of a multiple studies results. So when you have several studies and we want to perform a meta-analysis on those studies, then Cohen D's can be calculated, which is an effect size to do a meta-analysis. So Cohen's values can range as shown here. If it has a value of 0.2, then this represents a small effect size. If it is 0.5, then it's a medium effect size, and 0.8 or higher represent a larger effect size. Now, we have discussed and mentioned and described the effect size for the Hedges G, Cohen D, and the third one, which is an estimate size that can be used when the data are continuous, is called Glass's delta. It is a statistical method that determines a standardized difference between two group means. So it is similar to Hedges G and Cohen D, but it takes into the account the size of the control group. So it is calculated by taking again, as in Cohen's D and the Hedges G, the differences between the means of the experimental and the group, and dividing that by the standard deviation of only the control group. So there is a variation between the effect size estimate based on Hedges G, on Cohen's D, and on Glass's. If the sample size is very small, less than 20, then choose Hedges G over Cohen's D. If the sample size is greater, or sizes is greater than 20, then go for Hedges and Cohen's D both. If the standard deviations are significantly different between two groups, then choose the Glass's delta. So this criteria will make it easier to choose which one shall I go for. Is it Hedges G, is it Cohen D, or is it the Glass's effect size, or Glass's delta? Now, moving from continuous data, in which the mean is measured and the standard deviation, to a binary data that have an outcome which is binomial, which has two levels in it. So one of the effect size can be calculated using the odds ratio. It is used for binary outcome or binary variable. It measures the strength of the association between two binary variables, such as exposure and outcome, treatment and outcome. So it estimates the likelihood or the ratio of an event, or the odds ratio of an event occurring in one group relative to another. So this ratio of odds of an event occurring in one group compared to the odds of the same event occurring in another group is called the OR, or the odds ratio. This odds ratio is used in case control studies. So the OR values can range from starting from 0 and onward, 1 and 2 and 3 and so on. So if the value for the R is equal to 1, that indicates that there is no association between experimental control or between exposure and outcome. If it is higher than 1, greater than 1, plus 1, this indicate a positive association, increasing association. If it is less than 1 up to 0, then it's indicate a negative association or relationship. And the OR cannot be in minus, so the lowest value 0. So the effect size estimate, now we have discussed and described the effect size when there are continuous variables using the standardized mean difference, 3 different estimate size, Hedges G, Cohens D, delta, Glace's delta, and then we discussed and described the odd ratio for binary outcome, and now for a continuous variable and looking at a correlation between two variables, which can be represented by the Pearson Correlation Coefficient, or a standardized one, which is Fisher's Z. So the R will measure the strength and the direction of a linear. Here it has to be a linear relationship because we have two variables and they are in a linear relationship between two continuous variables. So the Pearson Correlation Coefficient R is the effect size estimate and is indicating the direction and the magnitude and the strength of this linear relationship. So the value of the R can range from -1 to 1. So 0 indicates that there is no relationship, no correlation, no association between the two variables, whether they are experimental or control. -1 and +1 indicates a strong correlation, whether it's positive or it is negative, inversed or it's an increasing. And so lower than -1 and lower than 1, that indicate variation in the strength of the correlation. So for Pearson correlation, rule of thumb, if the R is equal to 0.1, then it has a low effect size. If it is 0.3, then it is a medium effect size. And if it is 0.5, greater than 0.5, then that represents a larger effect size. Finally, when there are two variables and looking at the correlation between these two continuous variables, then Fisher Z transformation can be performed. It is a method used to transform correlation coefficient into a more normally distributed variable that can be used in standard meta-analysis procedure. The transformed values are then used to compute the summary for the effect size across studies. So Fisher's Z transformation can be performed or done when performing meta-analysis.